So yeah, this is my project. I'm super thankful for coming here to Jeju University Jeju Island. Does this work or not? There we go. And I'm really happy for my mentor, Shin, and his friends that have been helping me a lot during this project. About me, so I'm an independent consultant in machine learning, a data scientist. I recently graduated, or I haven't gotten my degree yet, but I'm finished and I will graduate soon. And I have a background in classical statistics. I actually started as a social scientist, but it was way too little empirical analytics for me, so I moved into frequency statistics. It was way too little math for me, so I moved into math, and it was way too little programming for me, so I moved more into engineering. But I think I've always thought of liking to combine subjects, and that's what the machine learning community is really good at. Using concepts from physics, statistics, and everybody are doing exactly the same things with different names. The problem that I've been working on here is what I did for my thesis, and I've been working on it and thinking about it too much, so I was happy to get here to do a reverse detox and just do it for a complete month. So before I came here, I had a thesis about this project. I had a bunch of ideas of what to do with it, and I had a GitHub repository with some code and some simple example and implementations on tiny data sets and only discrete data of certain shape. But what we've done here is that we've made this project into a 1.0 project, and we made some technical advances, implemented a lot of tests to ensure stability, and more examples. So, examples of what? Well, let's start with the problem. I came into this problem when I was thinking about when does sequences end? Trying to predict, for example, the big problem I was thinking about was customer churn. So you're trying to predict, will a customer drop off? And I think you can formulate this that it's a stepwise modeling process where you're thinking about it, and everybody walks through this. Because you're first thinking, what's the probability that a customer will drop off? Or equivalent would be, what's the probability that a person will die? Now, it happens. So it's an ill-posed question. So then you get into the next stage, what's the probability that the customer doesn't do anything for maybe 30 days? Maybe the customer doesn't buy anything in 30 days. And then you start thinking about, yeah, why don't we predict immediately how long until something happens? Like, how long until the customer purchases something? How long until this machine fails? And then you realize that when you think about it, that this probably makes more sense. And I will try to convince you why this is the case. And well, the big question is really, when will something happen? Because it's the kind of an inverse to when will something stop happening. And that's $1 billion question. A lot of applications to that. So in short, solution. We output the parameters of a distribution from the neural network. This distribution could be anything, but we chose the Weibull distribution, or I chose the Weibull distribution because it's really awesome, and I will show you that. And RNNs, they're really awesome too, especially for temporal problems. And the philosophy is don't try to like minimize your hyperparameters. Don't try to frame your problem in a too rigid way. Just be less hacky. And I think this is the key, to frame the problem in a sense, in a way that makes the solutions obvious. And as an example, how this data often looks like, I'm taking the Git logs from commits to the GitHub repository. And we can look at that. Oh, this is a very low resolution, but you should see, and yeah, this laser pointer isn't showing. Okay, so there should be small, tiny black dots here, and every line here is that like one first commit, and then they make a bunch of commits. And if we focus on, for example, it's lagging. Jeffrey Dean here. He made a commit here, and then so that was we didn't know back at that time, but we can afterwards say that it was 50 days until the next commit, and that goes down until the next commit, then another commit. So what you're trying to look for here is to predict the time to the next event, which is going to be like a sawtooth wave, the time until that one. And at the end here, we have a problem because we don't know right now how long time until his next commit. We only have like a lower bound on what it could be. And we realized that it's not a regression or classification problem. And the problem is due to what I call, or what's called in the oldest form of statistics, sensor data. And like, you will only find this in really boring papers, but it's an extremely interesting concept. We have a lower bound, and it stores information, and we want to use that to train our models. And the hacky solution is to transform it into a binary problem, to try to predict, so, okay, is something going to happen in the next 4 steps? I think this is the most common solution, but we have annoying hyperparameters, like how wide, how many steps are we going to predict ahead, and we don't get very informative predictions. We can only say, yeah, the probability that something will happen in 4 steps. We get some sparsity, we only have once here, so it's a lot very hacky kind of. So my proposition is this solution instead, a less hacky way to do it. It's a very, very simple concept. Predict a distribution over the time to the next event. So you can see it as just like it's a density problem. You're trying to, here we're learning that to just put a tight bound on this sawtooth wave. And at this end here, we will trying to also learn from this step where we don't really know when the time to the next event. And it actually finds it. So the trick is a clever loss function. If this is an observation that we've seen, if we're trying to push the density up there. If this is something we haven't seen, we only know that the time to the next event is higher than this threshold. We're trying to push the density over that. And since we have a lot of data points, we get some kind of compromise. And it works, in theory. Here we're only showing it that it's like before here or after here, and it's actually find the correct distribution. If we have 2 low resolutions, it's like here we only say the time to the next event was 0 or greater. It finds some kind of mean here. It doesn't really work. And the Weibull distribution is a really nice distribution to use just because it's closed form, so we can make it a continuous distribution or a discretized distribution. It's just 2 parameters. and it shows up in nature, just like the normal distribution, which is, means tend to be normal. Minimums tend to be Weibull. So if you ever plot distances between things or distance to things, you'll probably find one of these shapes. And it has some regularization methods. We can decide that we don't let it go too thin. So that's nice. So we predict the distribution. This is the key. We use some kind of survival loss from survival analysis, a very old concept to a new field. And we train recurrent neural networks that at every step, instead of a label or something, it predicts parameters that controls the shape of a distribution. And this is nice because we can make way more flexible queries to this. So we can predict, we can ask what's the probability that something happens within 30 days or 31 days. We don't have to specify that beforehand. And we get other things from this embedding, which actually makes sense. It's a 2D embedding. So we get some kind of interpretable output from this. And the vision for this whole project is that it should be simple, it should be generalizable. So I've always thought that, maybe Weibull won't be the optimal in some situations, so you can switch that out. So, more in detail, what we've done here, we've made a lot of documentations for the repository. We have a data pipeline to go from log files until the format that we want. Speed ups on the code at least 3 times. And rigorous testing, maybe it's a lot of tests, maybe not completely rigorous, but we're testing the important things. We Pipey installable package, I've scaled this up to bigger problems. The biggest problems with training this kind of things is philosophical and mathematical, but I've wanted to see stability when we have larger networks. It works. And I've had some examples that I can show you. How the pipeline kind of looks like, you would get some kind of data on this format. So you have some kind of ID. This could be anything, but it's just an ID that identifies the sequence. Then you have timestamps. Here is actually date, but it could be something else, and we could discretize it. And then you have a bunch of features. And then you select one column that identifies if this is an event or not. So we say here this is GitHub commits, so every row here is an event. That's what we say. So you transform it into this kind of plot. So you have a matrix with ones, and then you have a non-mask here. And then for every line here, you get a time to event, time to the next event. And then you get some sensoring indicators telling us, is this observation at this time step censored or not, to put into the loss function. Any questions about censoring, by the way? Or any questions so far? Yes.
What censoring is?
Yes. Oh. Okay. So, I think this might be this. It's a lot of slides. So censoring is, we are here. This is the data that we have. We have a sequence of events. And from that we can infer the time to event because it's just a countdown until the next event. And then we have an end of the data set. Like we query the data today, we get a bunch of records. So we know that we queried it today. We have the last event. And that means that when we are the day after the last event, we know that in the data set, it was at least this amount of time until the next event. Because this is the true event and we haven't seen it yet. Did that clarify? Let me push forward here. How far am I going to go? There we go. Yes. So we get a 1 if it's uncensored, 0 if it's censored. It's just a mathematical, it doesn't really make sense, but it's the other way around is less effective in implementation. And then we take also, at every time step, we have features. Like if this is a tensor, it can be a lot of features. And we also have whether there was an event in the last step. So we don't have to craft our own temporal features, which is, I wonder how much time that takes. And it's implemented so, like, we want the alpha parameter, that's a positive parameter. So I'm using, pre-initializing it with some scalar, then I'm taking an exponential of the output layer. The beta, that's like pretty much like sigma in the normal distribution. And I want to clip it, but I want soft clipping. So I'm using a sigmoid, and I bound it to say that it can only be between 0 and this initial value. And then you have the censoring indicators, time to event, and then you put it in a loss function. This is the discrete loss, but if we have continuous data, that's an even neater loss function. And in Keras, it looks like this. I wish it was more complex than that, but that's it. So let's check on some large-scale experiments then. So you have the data as is seen to the model, like this is a vector. If you push the non-mask over, we present it as it actually looked like in reality. So you have user 1, user 2, user 3, etc. And we get to have the censoring indicators. There's not a lot of censoring in this data set. And I train a stupid network here. I'm using the phased LSTM unit. Have anyone heard of that? It's a pretty cool recurrent unit that has a countdown built into it. But I use this just to get a nice embedding. So I had a deep but small network. And this is the prediction. So this is kind of a 50% of the probability should be within these bounds. Seems to make sense, right? And then we have things like this. This user was clicking on this website or logging in every once in a while. Then it suddenly stopped. And the network freaks out. This person isn't going to come back in a long time. So like this is probably where you would send out your email, right? And then it's a stability. They actually come back. Yeah.
What the fact that your prediction went up? What does it mean?
It means that at this step, we're here. It says that no, it's 70%. We predict that it's 0.75 probability that the event will happen within 175 days. And I think the interpretation is really that this is a large value, so it probably predicts really that it's not really going to happen. But we've never seen anything not happening because that's in a million years. So we get an embedding. The prediction here would be that every time step, so we get some kind of, this could be interpreted as the mu in the normal distribution. It kind of oscillates with weekdays. And we get how sure we are about our prediction, how tight the distribution is. And this is beta. So let's look at, if we pick eight users here, and just look at how the embedding will look like. So this is when we think, like at this point, how long time do we think that it is until the next event, and how sure we are. So they're like moving dots a little bit. It makes more sense when we take all of them, all the 26,000 users. The red here is if it's moving in that direction. And we kind of start to get a sense of a pattern here. First of all, it's moving back and forth during weekdays, and we get our churners here. The users that seem to that are predicted to take a long time to come back, and staying there. And the ones that we predict will be here in 10 days, or like in a very predictable future. And those that are here all the time, or going to be doing things all the time. We can look at TensorFlow commits, then they leave. So we actually, people here are predicted to many people are predicted to have commits within like 10,000 days. And this little tail here of a kind of a bloodstream of users that leaves into nothingness. While these are GFDs and whatever that are predicted to commit again. Yeah, this GIF was a little bit slow, but yeah, the tail here of dead users is just ramping up. So in practice, like I don't know if we would cluster in this space at this day and take actions based upon this. And then we could, of course, pick one of these users and just look at them, predict the distribution of the time to the next event, and use that. So when we have a lot of censoring, like people commit once, leave, we get stability during training, but the parameters get huge. It predicts like, yeah, it's 35,000 days in the future. That means that they're dead. So I don't know if it's a bug or a feature, but it also affects the predictions for users that will probably come back. Another thing is that we assume that the censoring process is independent from what we're trying to predict. But if it learns that, it can actually learn to push into infinity. And there's some solution for that. And I've tried another one, which is to actually try to predict, is this user at this time step censored, and then use that prediction to train or to weight the observations and then train the regular neural network. This is kind of an adversarial method. But if we don't have censoring, it also works pretty well. Like this was the embedding when I predicted on machines that would fail. Became a pretty apparent pattern. And this is like one machine that walks through a graph of different failure modes and then finally dies. And the prediction here would be like the final point of failure, and it should squeeze that using features. So if you don't have sensor data, it's just like a neat objective function, seems like it. If you do have censoring, it works well. And if you have a lot of censoring, it can cause problems. So the code. The repository is Pi2, Pi3. It's the TensorFlow objective function. The Keras layers and helpers. It's mainly a Keras repository so far, but the idea is to like any language. Data transformation and the general data pipeline with the idea of parsing any data frame and put it in the right format. But that's in production or in process. It's visualization utilities and documentation, example implementations. Yeah, so we have the GitHub site, we have the documentation site, and a bunch of examples. so there's a lot to do. There's still work in progress to fix and understand what this means, and continuous data, so we don't need to pad out between sequences. But it's fun that some people actually seem to be using this. I got this 3 hours after releasing the 1.0, so that was a lot of fun. So I recommend pip installing this thing, and a big thank you to everyone. So the regularization methods for the artifacts, the common way to do it in regular regression when you're doing regular survival analysis is to train a similar network, or similar, like a regular regression model for it. So this is basically what I tried. But I've also tried, just like removing obviously dead sequences. But that felt like a hack, so I wanted to do it automatically, because when is it obvious that a sequence is dead? I don't have a general answer for that.
Because I was thinking maybe conditional random fields could be a really good use case, because in that case what we could do is try to predict a chain of transition probabilities. That would then determine how much of the gating effect should be constituted into the learning model as you reach closer and closer to a sensory point. Yeah, so that's a good
idea. Yeah, thank you.